And, and one of these, EcoLexicon, is very much Pilar's project. EcoLexicon is a multilingual terminological resource in the field of environmental science, but it's much, much more than just a dictionary and a corpus. It's a very, very rich resource of great potential value for users involved in both text understanding and text generation. People like translators, environmental scientists, and so on. While it does build on existing technologies, it also extends them in really interesting ways. Notably, for me, in the use of semantic sketch grammars, which can extract semantically related pairs of terms from its corpus and generate semantic word sketches, and thereby populating a complex and highly informative conceptual network. When I and the other trustees of the prize were evaluating the applications, EcoLexicon really stood out as a truly impressive piece of work. It's original, it's innovative, it's designed with the user in mind, and it's very transparent too. The technologies which it has developed have been made available in the public domain. And all in all, we all felt that it was exactly the kind of project which Adam himself would have become very excited about. So that's enough from me, and I'm now going to hand over to Pilar. So thank you, Pilar. The microphone is yours.
Hello, good morning. Do you hear me well?
Okay. Yes.
Yes.
Thank you, Michael, for this very nice presentation, and thank you also to eLex organizers for having invited me today, and I would also like to thank the rest of the audience for being there this morning, despite a long, tiring virtual year. So I'm going to share my screen. Okay. And okay. So as Michael said, I come from the University of Granada, and more specifically, I work in the lexicon research group. And I have to say that EcoLexicon and byproducts have been the result of a team effort. So I would like to acknowledge the role of the rest of the members of the team. I will talk today about EcoLexicon, how it was conceived, designed, and populated, and also the byproducts that came along with while developing it. I know that especially EcoLexicon has already been presented in a few conferences, and some of you might have already heard about it, and nearly all I have to say today. So in that case, I apologize, but I also encourage you to make any suggestions for improvement. So this is the outline of the products I'm going to talk about. First of all, EcoLexicon, which is it's a terminological knowledge base on the environmental domain. So far, it has more than 4,400 concepts and more than 24,000 terms in English, Spanish, German, French, Modern Greek, Russian, Arab, and Dutch, though not all languages are equally covered. In a nutshell, this resource has conceptual, linguistic, and graphic modules, and the users targeted are all those involved in environmental communication, such as translators, technical writers, or environmental experts themselves. I will also talk about the EcoLexicon semantic sketch grammar as a way of extracting special knowledge. It was a tool that we developed for ourselves, but finally we shared. And it serves the purpose of extracting semantically related term pairs. It is composed of 64 sketch rules in English and 61 sketch rules in French, based on knowledge patterns, and that I will talk about. The users of this grammar would be those interested in obtaining semantic word sketches from their own corpora. Then the next step in this logic we followed was sharing part of all of the resources we're creating, not only EcoLexicon, but also the corpus that was being useful for us, where we were extracting the information and employing the grammar. So this corpus is made up of 23.1 million words in English. It has some metadata that classifies the corpus in different text types based on domain, user type, geographic variants, editors, years, and countries. The users of this corpus will be those involved in environmental communication, such as translators or experts. And finally, I will present EcoLexicon, which is a different tool that we build in order to reuse EcoLexicon and other resources, such as BabelNet or IATE, etc. So it is a terminology-enhanced computer-assisted tool, and it is aimed for environmental translators. So EcoLexicon. EcoLexicon is the practical application of frame-based terminology, and frame-based terminology theory by Pamela Faber, my academic mother, is a cognitively oriented theory of specialized knowledge representation that emphasizes conceptual organization, multidimensionality, and knowledge extraction from large corpora. It is inspired in the very general notion of frame as described by Fillmore, that says that a frame is any system of concepts related in such a way that to understand any one of them, you have to understand the whole structure in which it fits. So this very general idea of frame permeates all of the modules present in EcoLexicon. Our aim is that our users acquire knowledge rapidly, and we are based on the assumption that knowledge acquisition occurs when concepts are related to each other and linked to previous knowledge, and not when terms are only arranged in alphabetical order. So this is EcoLexicon user interface. In this main area, you can see the conceptual networks, which are a big part of EcoLexicon, where concepts are related to others based on semantic relations and all. Then we also provide corpus access from the same platform. And then in this site, you can see definitions that are also linked to other concepts present in the knowledge base. The different terms and variants in different languages that are associated to the concept, which means that this resource is concept-oriented. Then we also have some other resources, such as graphic resources, images, then conceptual categories and physiology. So if you click in one term, in one of the terms, you will get some information, and also a link to the concordances in the corpus. Then images are chosen. Usually there are several images describing each of the concepts, and they are chosen based on the semantic properties activated in the networks. In the phraseological module, although we are still working on this and we are modifying this module radically, so far you can see in some of the entries, you can see that verbs are not a concept entry themselves. They are associated to the entries of the arguments they take. So they're classified in different conceptual dimensions and they're clustered together. All of this information in EcoLexicon is manually created, and it is semi-automatically extracted from the corpus, right? So I'm going to talk now about the problems we encounter. This problem so far has been information overload. This is an example of how our main aim, knowledge acquisition, can be compromised. Because, for example, here you can see water in a network that is not meaningful at all to users. Users could only extract from here the fact that water is all over the place in the environmental domain. But the thing is that all of these conceptual propositions that were manually introduced in the relational database underlying the application, all of these propositions are true. they have been extracted from the corpus. And of course, water is a very general concept that is involved in many different processes in the environment. So this is because a concept can be framed from different perspectives, and this is called multidimensionality. So in the same way that we can imagine, I mean, when we activate the concept of water in our minds, it depends on whether we're seeing water as a resource, as a drinking fluid, or as a chemical compound, or as something involved in the Coriolis effect. Okay, so multidimensionality is especially present in environmental concepts. Okay, because the environmental sciences are a broad domain, and because concepts themselves are quite dynamic. They can be agents or patients in different processes where they are involved. So in this sense, the challenges stated by Bowker already in 1997 are the following: discover the motivations of multidimensionality, when it occurs and why, assess dimensions relevance before representing knowledge, and find a way to represent multidimensionality in the resources. So this is what we try to do. So in the same, excuse me, in the same way that our brains need more context to retrieve which concepts are more saliently related to water in each scenario, and we do it naturally and no problem, we wanted to do the same in a representational system. So we adopted different strategies. The first strategy was only a quantitative strategy, which means helping the user getting rid of so much information with some settings. For example, they can choose which relations they want to show in their network so that not all of them are shown together. They can also restrict the graph depth, and then instead of seeing the two hierarchical levels that are displayed by default, then only one. And well, they they can play around with the network. Okay, there is another way to play around with the network, which is from the standard mode of visualization. You can, for example, remove any. You get all of these options clicking the right button of the mouse, and you can remove any concept that is bothering you. And here also you can remove or activate different relations based on whether they are hyponymic, meronymic, or non-hierarchical. Okay, so this is another way of restricting information. This only shows hierarchical hyponymic relations, and it is displayed on a tree mode, which can be clearer than the other kind of networks. And this is another very different network called the path network, where you can look for two concepts and two different concepts and look for the shortest path between them. For example, between hurricane and sand, if we want to know how they can be related, then we can see how. And this should be clearer. But of course, you have to know, you have to want to look for two particular concepts. Then we adopted a second strategy, and we created, we tried to refine the networks where a lot of different children concepts were activated. For example, instruments. There are a lot of instruments in the environmental sciences. So there were several umbrella concepts that were created. These concepts are somehow artificial because they're not like true specialized concepts, but they only serve the purpose of classifying information. So in this way, instead of having all of these instruments, children scattered in the same node, we decided to create certain different boxes based on these umbrella concepts. Okay, but of course here, all of these subtypes or hyponyms are related to instrument based on the same semantic relation, that of functions. When we don't have the same kind of relation, then the strategy, the third one, is to specify hyponymy. This is not yet implemented, but will soon be. And And in this case, you have the example of sediment types. Sediment types are all hyponyms of sediment, but they are based on different dimensions. So in that case, maybe the hyponymy relation should be specified. And there you have 5 examples of a more specific type of hyponymy. And then we adopted a 4th strategy based on, which is more similar to what we try, what we naturally do in our brains, which is reframing and recontextualizing concepts based on a particular scenario. So here, context would be assumed to be domain-based. Okay, so since environmental sciences has different sub-areas, then we divided the whole domain in different sub-areas, such as those you see here. And now all of these propositions in top-level concepts that are particularly prone to information overload were assigned to each of these particular domains. So in this case, the information is constrained, and instead of showing this whole non-meaningful network, we show this other network, for example, in the case of sand, in the wastewater treatment domain. For example, here sand is a type of mineral, even a type of waste, or a type of settable solid, and it is related to very different concepts than as compared, for example, in the geology domain. Here, sand is more viewed as a patient in different processes, filtering processes, for example, whereas in a geological context, a much more active role, or maybe a meronymic role, more outstanding. Okay. So this is also applied to definitions. For some of these concepts, we have several definitions. We have like a very basic definition, a global definition for the whole environmental domain, but also we specify the different slots open in this definition structure are filled with different values according to the domains. For example, sand can be, is much more often considered a kind of sediment, and in soil sciences, it's considered rather a soil component, or in civil engineering, it is actually seen as a natural construction aggregate. So changes appear in the genus itself, but also in the differentiae. Okay, so as you so definitional definitions in EcoLexicon are based on different templates based on the categories to which concepts belong. So the definitions make category membership explicit, and they follow a systematic pattern. Okay, so this is a non-contextualized definition of growing, but based on the template of hard coastal defense structure, which means that groins, revetments, breakwaters, seawalls, etc., will be defined and following the same structure. So as you can see, semantic relations in EcoLexicon are the cornerstone. Okay, especially in the first phases of the project, where conceptual information was our priority, based on that initial aim I talked about, knowledge acquisition. So these semantic relations were extracted from our corpus, following the usual methods in terminology based, for example, in knowledge patterns, which are the structures in natural language that convey explicitly these semantic relations. Here you have 3 different patterns for hyponymy, but also looking at multi-word terms. For example, in aquifer sediment, we can say that we can extract the encoded relations, which are aquifer sediment is a type of sediment, and sediment is located at aquifer. So this is where the EcoLexicon semantic sketch grammar starts. We, after manually searching the corpus year after year, we developed this grammar to semi-automatize the project. So knowledge patterns in terminology are used by many authors and projects, but it is still a time-consuming manual work because there are no user-friendly, to the best of my knowledge, publicly available for non-computer users, I mean. So knowledge patterns can be formalized as local grammars and help in the systematic study of multidimensionality and concept behavior, concept variation, fuzziness, etc. So we developed these knowledge pattern-based sketch grammars in Sketch Engine to fill this void, and for our own work in EcoLexicon, in order to improve the networks and the process of definition construction and template derivation, etc. In order to be able to get semantic word sketches in our corpus, and also we decided to share the grammar for other users wanting to get ready-made word sketches in their own corpora. So this is how semantic word sketches look in the old interface, I know, of Sketch Engine. Here, you can see that there are 5 different semantic relations. So we derived we build different grammars for different relations. And the process for building these sketch grammars is as follows. First of all, we collected the knowledge patterns referenced by other authors or those that we extracted during the construction of the EcoLexicon. It is also a recursive method because once we collect these patterns, we can also extract new term pairs, and then these new term pairs can be reused to get new patterns. Then they are grouped together and we decide whether they should be split in different sketch rules or put together. For example, the typical hyponymic knowledge patterns such as and other cannot be together because hyponyms and hypernyms occur in different sites of the pattern itself. Then, of course, we refine the grammars by adding adverbs, punctuation, maybe modal verbs, relative clauses, and non-greedy queries for enumerations. And then we validate each of these rules by enriching it with optional elements we hadn't spotted at the beginning, and then we refine, detecting false positives, etc. So it is always a balance between noise and silence, or precision and recall. So these 64 sketch rules are divided into 22 hyponymic rules, 18 meronymic rules, 12 causal rules, 4 related to the location dimension, and 8 for function. And these are the kind of patterns that, well, simplified, that we collected. This is only an example of only one sketch rule within the sketch grammar. Here you got the first element would be the hypernym. The hypernym is classified into different types. So here you have the position of the hypernym, and here you have the position of the hyponym, which must be a noun, but cannot be any of these nouns. This was included in order to, well, to avoid noise, okay? Then you have the pattern itself. The anchor pattern is here, which has also optional elements. We can find the verb to be, or maybe a comma, followed by classified or categorized, and then followed by in or into, and between categorized and the preposition, you might have another preposition and different elements. Between the hypernym and the pattern itself, you can get also different punctuation marks or relative clauses and modal verbs, etc. So thanks to this sketch rule, for example, we get these occurrences of hyponymic structures. So my climates can be classified into 3 subtypes, or can be classified into 3 large groups. So you can see that here there is another element as compared to this case, which was accounted for in the grammar. here also you can be classified into one of the three major groups. So here also, thanks to the possibilities of regular expressions and post-tags, we get these slightly different cases of patterns. But of course, this approach has certain limitations. For example, sometimes the hyponym is a general word and it's of no use for us. For example, here, although the numbers refer to aquatic species, then between numbers and species, there's no valid relation for our knowledge base. Then we can also get a hypernym that refers to something stated later. For example, here, species was identified as a hypernym of river, and actually the true hypernym should be physical barrier. So we analyze all of these noise causing structures, and we try to refine the sketch grammars later. Then we also have some cases that are not untrue, but they are located by mistake. For example, here species is the hypernym of Mulus surmuletus, but it is only by chance, because actually, well, the hypernym should be grazers. Then also we have some unavoidable mistakes based on post-tagger mistakes. Here, for example, form was tagged as a noun instead of a verb. So here there is some false positive. We also have cases of anaphora. We also have polysemic knowledge patterns. For example, here you can see in two sentences where formed by activates different relations. For example, delta cause formed by deposition, it would be a causative relation, whereas here the cuspated delta was formed by alluvial sediments, we'll be talking about meronymy. The main problem in the sketch grammar so far is the fact that we cannot integrate multi-word. Well, we haven't integrated multi-word terms within the grammars because it's quite. I mean, it's harder. So we get some results where rocks are categorized as a type of rock. I mean, rock has the hyponym rock because in sentences like this, alkaline rock, including pyroclastic rocks, if word sketches were included multi-word terms, then the hit would be okay. Then we also have something related to multi-word terms, which is this example. Stones are classified into three main groups: igneous, sedimentary, and metamorphic rocks. Here, in natural language, we can actually spare the reader and not make him read rock 3 times. So in this case, we would have some silence. Okay, here igneous rock will not be activated as a or identified as a hyponym. And also, we have to bear in mind that texts do not reflect perfect taxonomies. For example, we can find things like T-head groin. A T-head groin is a structure that whatever. And even though the correct structure would be, I mean, the useful representation would be T-head groin is a type of groin, which is a type of coastal structure, which is a type of structure. But in the texts, we can see sometimes a concept linked to some grandparent or even a grandparent and all. So there is not a perfect hierarchical structure conveyed in the text. And some of the times also there are like ad hoc hypernyms because of how, depending on the context. For example, we can say that T-head groins are an obstacle to whatever process on the beach. And here, obstacle maybe should not be chosen in a terminological knowledge base, or maybe yes, it depends on the results on the corpus. But this is where terminologists have to do their post-editing creative work. So, and also we have to take into account that explicit knowledge patterns do not occur for all hierarchical levels. For example, when we have compound multi-word terms, saying that, finding a sentence where we say that T-head groins are groins that whatever, this is quite redundant, because in the term itself, we can infer, the reader can infer that a T-head groin must be a kind of groin. So in that case, we have to look for modifiers and analyze multi-word terms in order to complete the lowest levels of the hierarchy. And this is why we made new grammars in order to find to make multi-word terms available within the word sketches. And these grammars were reused in the other grammars based on the knowledge patterns in order to integrate again in these semantic word sketches the multi-word terms. So once we designed the grammars, and once we developed the corpus and all, we decided to make it available for different users. And of course, it is as an open source and an open corpus in Sketch Engine. And of course, there you can do whatever you can do in Sketch Engine, you can do with our corpus, with the particularities that in our case, the metadata are those that were useful to us. And so you can choose and constrain your searches by these different metadata. For example, based on domain, which are the same domains that are used to constrain the networks, based on the kind of the genre, the text genre, based on the kind of editor or language variant, countries, users, etc. So here, for example, you can see a word sketch of water in coastal engineering here and water treatment there. So here you can see that, for example, the types of water, shallow water, deep water, fresh, coastal water, are quite different to drinking raw ozonated groundwater, or the kind of verbs that are used as with water as an object are also quite different. So this is quite practical for us as researchers in EcoLexicon. Of course, the semantic word sketches are also integrated here, so you can see and study, for example, how categorization varies across domains. And you can see, for example, that nitrogen is a type of nutrient, element, or chemical in the meteorology domain, as compared to a molecule and pollutant in the domain of chemistry. You can also see things like, you can also search for frequencies and the verb liquefy. You can see that it is in soil sciences and expert text where it is most often used, etc. But it is a corpus, nothing else to tell. And finally, we have this terminology enhanced computer assisted tool where you can, this would have been more practical to show in a demo, but I don't trust our server, so I did some screenshots after. If during the questions that we have time, I can show you. But here, it is based on MatePad, which is an open source tool, and it is connected. This is the editor where translators would do their translation. It is also equipped with machine translation, so translators can translate or post-edit. And so this segment here, the original segment, it is connected to EcoLexicon, and all of these terms in yellow are found in EcoLexicon. So if you click here, you can display all of the information you get in EcoLexicon, and if you click here in green, you can display all of the information that BabelNet stores regarding each of the terms. Here you can see how you can interact from the source or target segments. You can look for information in all of these resources, EcoLexicon, BabelNet, Sketch Engine, our corpus, and IATE, and also other resources such as Wikipedia, Lingua, word reference, etc. And this is the kind of information you get in all of these resources. I will go fast because I'm seeing that I don't have much time now. And so in BabelNet, for example, you can see definitions, equivalents, and compound words, images, etc. Of course, you have to bear in mind that this is not context, I mean, BabelNet is huge. So here corrosion, it's maybe not related to erosion, but it is offered anyway. And then equivalents also are not refined, but since it is a huge knowledge base, then it is very useful for translators. Then you also have images that can complement those offered in EcoLexicon. And here you see how the access to corpus is shown. You can see concordances, you can also do some CQL queries, and you can also access word sketches, default word sketches and semantic word sketches. And here is how the information is shown, and here is how other resources are shown, and users can also add new resources on their own if they have the right URLs. We did two experiments to evaluate this tool based on user expectations, behavior, performance, and satisfaction. And the two experiments were comparing how these variables, but in MadeCAD or EcoLexicon translators, and in EcoLexicon translators and post editors. And so we saw that they clicked, especially in all of the functions in EcoLexicon. And we also saw that translators and post editors prefer the definitions and translations options, not much compound words or corpus access, maybe because they don't know how to use corpora. And we also, in terms of performance, we saw that post editors were, that EcoLexicon translators were faster than MadeCAD translators, and post editors were also faster than EcoLexicon translators, as it was not surprisingly. But in terms of performance, when comparing MadeCAD and EcoLexicon users had a better quality in their assignments. But in the case of integrating post editing, machine translation, even though they were faster, they were not necessarily better. Okay, so in that case, quality was better in EcoLexicon with no machine translation. So I'm going to finish very soon. This is just, I just wanted to tell you what our current and future plans are. As you have seen, conceptual organization has been the most important facet of EcoLexicon. So now we are evolving into a more, a thorough description of terms, term variants, and a systematic study of equivalence. Now this is only a prototype, but we are developing a different module where terms are better and more exhaustively described, where different translation variants are accounted for and are ranked according to different parameters. They are described according to morphological changes, reductions, extensions, etc. with regards to the main term. They're also shown in context, in a conceptual context for cognitive variants. For example, these are all the variants for photochemical smog, and you can see in Spanish, you can see very different perspectives on the use of terms and whether the head or the modifier is what changes, or the conceptual dimensions that each of the terms emphasizes. And here you have like the description of individual terms with specific notes on how to use them, because if we are going to account for terminological variation, we need to make users aware of when to use which term and why. Okay, and in a recently funded project, we're now expanding EcoLexicon to have the representation of culture in a transversal way, because we want EcoLexicon to be inclusive. Okay, so now we're going to integrate named entities, because I mean, all bays do not, I mean, even if bays are described as an abstract concept, then when we look for particular bays in the world, they participate in very different processes. So named entities are going to be included. Definitions are going to be reformulated based on specific cultural parameters. For example, here, lionfish can be defined as a genus of venomous marine fish native to blah, blah. But in a Caribbean context, it is mostly a predator. Okay, so in the same way that we did the flexible definitions with domains, we are going to do that with cultures. And this will also be applied to images. For example, here you have two images depicting the same concept, which is coral reef, but this one is in Scandinavian countries and this one in the Caribbean. So also as a future line, we would like to apply frame-based terminology to other fields and projects with different needs that we have already done. One is with the Spanish Army. We did like a kind of EcoLexicon, but for the Army, according to their needs. And the Humanitarian Encyclopedia is another project we're working in. And actually we have a demo at 11. And just two final remarks. I would like to highlight the role of the lexicographer terminologies in this post-editing, big data, machine learning era, because I have the impression that sometimes lexicographers are underestimated. We even underestimate ourselves because we are overwhelmed by the quantity of information that can be given by the machine. But at the end of the day, I think it is the human being who is involved in the decision-making process, in the creative part of the process. And sometimes also there are certain things, certain nuances that can only be understood by the human being. So I would like to, embrace technology. Technology should make our life easier and especially accelerate the process of extracting information and representing information, etc. But it is also important, I think, to join forces and promote collaboration between human beings, because it is true that developing a lexicographical resource takes a long time, and maybe a true multidisciplinary approach with a lot of agents involved could be the solution, both human and artificial. So thank you very much for your attention. I'm sorry I took all of the time except for 1 minute, but if you have any question, I'll be glad to answer it. Thanks.
I don't think you can see me, actually. I haven't got my video on. Can I do that? Nope. Okay, well, thank you very much, Pilar, for a very clear introduction to your brilliant project, really ambitious project. And oh, hold on, here's my video now. And it's great to see that you've got even more ambitious plans for the future. The thing that struck me was how at every stage you've really thought hard about the user, the end user, what the user needs, what they can cope with, and how to make it easy for them. So as well as being a technically brilliant project, it's got the user at its heart as well, which is something that I really approve of. We have got time for one question, which comes from Noe Gasparini. It's in the chat there, and can I hand over to you, Noe? It says this is an impressive piece of work. Is the ontology available somewhere? Okay. Etc.
Well, the ontology is not available. Well, because there have been like 2 versions of the ontology when we changed the approach to category membership and all. So the ontology exists, but still, since and this is why I want to ask for more collaboration. We depend on computer scientists to make the new version available and facilitate this public Sparkle endpoint, but it is definitely something we want to do, and sooner than later.
Okay, thanks, Pilar. I'm sure everyone will agree that Pilar is a very worthy winner of the Adam Kilgareth Prize. This year was the third iteration of the prize.